Well, thank you for sticking with me through the false advertising and everything. This will be some motions towards a six-puncture formalism, without declaring a full six-puncture formalism. And I'm just going to talk about some stuff that's probably not quite in its final form. That came out of a discussion session with Sana, Arpan, and Andy over the last year at MIT or so. And what we're going to talk about, as I will explain, is very much inspired by the work of Hudson, the work of Matthew Mondal, and also relies on some intuition coming from projects of Hoffman and Hoffman. All right, so what have we learned so far? So R is a nice ring. The discrete quasi-symptomic ring. But also many other things. For example, KU. Then those are notes, the echelon, which is given by the limit over all maps from K to A is even, and we start with possible totality. And this is true both if you think of THH as just in the infinity ring, or if you think of THH as coming with all sorts of structures, such as a circle action and Frobenius, in which case you'd be looking at maps to A that respect the circle action in Frobenius. But this theory works very well, with the one caveat that it's usually not a good thing to do when the ring is not somewhat nice. But as we've seen, for example, in Matthew's talks, we would like to have a theory for all kinds of rings. We would like to have a theory for even spectral schemes, for some flavor of spectral schemes. And that theory we expect to somehow be left con-extended from smooth things, or perhaps determined formally in some sense from the quasi-symptomic case. But it takes some work to figure out what exactly we want that theory to look like and how it will be formally determined from a quasi-symptomic sort of case. So I want to ask the question, what sort of spectrological geometry interfaces with mosaic fluctuations? I want to have in mind some kind of class of spectral schemes that's very general, for which I can study some kind of associated graded on their topological cyclic homology. All right, and so let me make a definition. And even this stack the counter not all infinity rings, but even in infinity rings, the space is the category of even three states. Is denoted by functors from even infinity spaces, in the sense that I want to think of morphisms as just being natural transformations. So I'm trying to define algebraic geometry where the test points are spectra of even E-infinity rings and not spectra of, say, other kinds of E-infinity rings. This might be a little bit strange, but I want to convince you that it's something that comes up very naturally if you're, for instance, interested in Blavatsky's theory of motivic spectra. Also, of course, it's something that interfaces well with the philosophy from, say, the chromatic Mosanzat's paper. We could restrict even the infinity rings to just Navier theories and extract invariants of sort of other flavors of spectral algebraic geometry. Okay, so what is the main example? Except we even preset. If R is any E infinity ring, not necessarily even, then we look at the even spectrum of R, speed R, and this will be some functor, and it will take in an even E infinity ring and produce the space of maps from Y to A. So if R is itself even, this would just be representable in even presets, but R might not necessarily be even. We can still talk about its speed. It's an even spectrum. So there's some invariants one can extract in even preset. There's unique. Net preserving model techniques something does what it affects the representables. You can take the global sections, and the result of that will be a filtered, the infinity ring. I want the global sections, the speed of R to be speed infiltration. This global sections functor will take in a even preset and spit out a filtered the infinity ring. When you plug in speed of something even, you're supposed to get the double speed Plasnikov teller, and then we write constants to define global sections in general. All right, another invariant that you can extract from even preset is its underlying classical preset. Well, if I'm given some functions, and even in infinity means to places, and I call X, we can ask what this is some kind of spectral stack or spectral pre-stack. What would be its underlying classical pre-stack? Well, there's a functor due to the category of graded commutative rings. And here I'm taking pi star, and so since these are all even, when I say graded commutative, I'm not saying anything funny about equitable sign rule. I'm just saying this classical commutative ring, but coming with a grading. And I can extend this thing, I think, is a left extension, and this will then be the underlying classical set. It's just a three-stack in the sense that it's a functor from commutative rings to spaces, and the grading means it comes equipped with the canonical line from an example. But look at the functor from even E infinity rings to spaces, which takes any ring to a point, and that's called speed of the sphere. Right? So speed of the sphere applied to some ring A takes A to a space of maps from S to A, which is contractible because S is the initial object in the infinity rings. And I can take the underlying classical preset. And the result of Hahn says that this is the moduli in the groups with the unloaded with this lead algebra.
the global section funds are part of some junction that we would usually expect.
Yeah, it would be part of some junction, which you might get to, there's various junctions landing in, depending on how structured you think of global sections, you'll have lots of that joints.
Where does this one land?
This one, just for example, naively, you could say that lands in filtered spectra, but we'll try to make it land in a more structured place than this filtered spectra.
What is underlying das du hier again?
The moduli form of roots. Like pillars. So let me just point out that to understand in a sort of good categorical way, symptomic homology, the classical schemes it's helpful to view them as sitting inside a larger class of objects that have perhaps better formal properties, namely to view them as interfaces of derived schemes. Usually derived algebraic geometry, and they have slightly better formal properties. So what is this theory of derived schemes? It's some kind of algebraic geometry based on these derived rings. We'll talk about that in a moment. And the main point of this talk is supposed to be that I want to introduce some category that plays the role of derived rings in spectral algebraic geometry. And that category I'm going to call synthetic infinities. And so this category is some kind of generalization of discrete rings. And this category would be something like generalization of even the infinities. But there's going to be a very tight analogy between these two categories, and I want to credit Mark on that for really bringing into my mind how tight the analogy is between these two categories. So in particular, when you think about derived rings, there's usually two kinds of them. There's the co-connected derived rings and the connected derived rings. And they have different theories attached to them. There's co-connected derived rings, connected derived rings.
You were using it twice.
And the connected derived rings are what are called animated rings. They are formal geometric realizations of polynomial rings. From performing some formal cyclic code and procedure to the polynomial rings, the co-connected ones is a kind of maybe more subtle fact that is very interesting about them, which is like they embed fully faithfully by a contravariant functor in classical respects. So this is the theory of affine stacks that's due to Solana originally, but then also written about in detail by Lurie and in a very useful recent work on and what we're going to do is port this theory over, following as much as possible the presentation here. So, co-connected synthetic key infinity rings, whatever that means, you don't get any of it. We should be guided by the philosophy that they should embed fully faithfully by a contravailing functor in even respects. And functors from even the infinity rings to spaces. And the connected ones is nonsense formally animated co-connected ones. Okay, so in a moment I'll actually write down the definition of a synthetic the infinity ring, but for now let me make one additional remark. More codifying. Welcome. Based on work in progress. Parkman and Hawkins. Proves he concludes synthetic infinity rings that fully faithfully motivic norm spectrum category that was defined by Bachman and Boyle. So, of course, a lot of people, in particular Robert, have developed quite a lot of ideas and theorems and intuitions about C motivic norm spectra, this theory that is defined in the motivic category of Blavatsky and Morel. Our goal with this project is just to take all of these hard theorems and try to turn them into definitions and therefore absorb them along the way and learn how they all tick. Yeah, we're going to try to avoid using anything about these previous definitions, and it will require some sort of hard work in progress to relate them. But of course, the intuition for what's supposed to be true all comes from this work that we're doing. Okay, so yeah, maybe I'll just reiterate that this might sound like some crazy thing. You might not believe it's very natural. You might have just made it up. But we're in a good situation in the sense that we're going to be rediscovering something that is already defined from an entirely different point of view. All right, so maybe it's about time that I try to define this category of synthetic E infinity rings. So if you want to define animated rings, what you have to do is define the free ones, and then you take formal sifted coordinates. You look for free objects, and so let's make a definition of what a free synthetic infinity ring should be. For n less than equals to 1, define the free synthetic infinity ring and the bi-graded sphere and n. Again, coming from some kind of motivic homotopic theory language. But anyway, this may be just some formal symbol, bi-graded sphere and it's going to be a functor from even infinity rings to spaces. What functor is it? It's the functor that sends an even infinity ring R to B to n plus m loops infinity suspension minus 2n. So that's just some functor. And if you think about it, it shouldn't be too hard to define what a free algebra does in terms of its maps to other algebras, and that's what we're doing here. So we're writing effectively what it means in the motivic category to give a map from this phi-graded sphere to an object without any structure in fiction. Okay, but we can make this definition, and the point is that that we want to describe not just what the free objects are, but all the maps between them. And we're describing that by saying maps between them should have something to do with natural transformations of functors. And it's all guided by this idea that these co-connected things, and the free ones will be co-connected, should just be viewed as presets. And that should tell you what the maps between them are as well. Okay. So similarly, let's define free on a wedge of spheres. I have some wedge of spheres. I'm not going to do anything particularly scary. I'm just going to look at the functor, sends a ring to a product of free. This and just the product space. All right. So define some category C. So its opposite category is the whole subcategory of even presets on the above specified even presets. So there's only one fiddly thing, which is that Steve is supposed to be contravariant, so there's some complications. Here, definition. Synthetic infinity ring is a functor from this category C to spaces, which reserves products and Cartesian squares of particular form. These three functors are not totally independent of each other. There's a pullback functor from root to infinity minus 2nr. Pull it back. I'm supposed to get the other thing from our list of free functors. And so I want to remember that these are related by asking that a synthetic E infinity ring also preserve these Cartesian squares. So this is a process of animation. I've taken the free things. In this case, I took the free things on all co-connected spheres. In a way, I'll make precise in a moment, but this n less than or equal to 2n condition was a co-connectivity condition. I'm looking at the free things on all even spheres, and then I'm formally adding, or on all negative spheres, then I'm formally adding shifted colimits. And if I try to define animated rings in that way, I would be doing something like looking at three rings on all negative spheres, not just S0, and trying to animate that. And so I would need to relate these negative spheres to each other in this way, even if I were just trying to define animated rings using three derived rings on negative spheres rather than just polynomial rings.
Can you just try to elaborate on why this deserves the name free thing?
So if I look at the functor that maps the free thing to some synthetic E infinity ring, that should not remember that the target was a synthetic E infinity ring. It should just be mapped from SMN to the underlying motivic spectrum. And that's the formula for maps from a bigraded sphere into a motivic spectrum.
From a vibrating sphere.
Yeah. I'll say in a moment, I think the next thing I was going to write is how to write down a forgetful functor to motivic spectrum, which may make it a little clearer.
In the derived rings case, do you get the co-connected ones by freely adding co-shifted limits? Or is it not quite as easy?
I think there are some theorems to the effect. Maybe the most interesting thing is that these can be combined into single categories.
Yes.
Not looking very big time. There's the forgetful functor. Synthetic the infinity rings before the spectrum. Which in the nth position of this filtered spectrum means R to spectrum made out of one, three, and R, and varies. The fact that we have those pullback squares being preserved tells you that you can assemble a spectrum as you vary this variable. And then there's a tau map, which makes this not just a graded spectrum, but a filtered spectrum. And the tau map arises from the canonical natural transformation. U squared, yeah. You take some space, you loop it twice, and then you bar it twice. That's like taking its second connected cover, and the second connected cover maps back. Okay, so that gives you some map to filtered spectra. With a little bit of thought, this could be upgraded to a map. These synthetic infinity rings to E infinity those by E plus multiples in the spectra, or in filtered spectra. And so this is an E infinity algebra object in the Slavatsky category. These after key completion, these results of GIK on. All right, and then the first theorem I wanted to write down,
Sorry,
yeah,
you mean it's modules over the logarithmic sphere, or can you have the algebras in modules?
I mean, E infinity algebra, so first of all, it maps, it gives you a full circuit S module and not just a filtered section, but it actually gives you an infinity algebra object in the modules. And here I think that, out in the sim, we go monadic, comonadic over one infinity equals W. So. So this is a statement that was noted by Hahn a lot in the motivic context with their motivic definition, which is not at all obviously equivalent to this definition. But that we were able to prove this, and so this kind of thing in particular says both products will push out synthetic infinity rings on this may be familiar in the sense that if you take an animated ring, the tensor product of animated rings is just the tensor product of their underlying infinity rings. Another situation which shows up with the delta rings, where the tensor product of two delta rings is just the tensor product of their underlying rings. This is a similar flavor. I guess another place this shows up is n infinity algebras in covariant entropy. I wanted to say the co-connected synthetic infinity rings have some kind of interpretation inside even these stacks. I should tell you what co-connected means. And the definition. The data spectrum is co-connected. The ith piece of X is 2i co-connected. This defines a T structure on braided spectra, and then for filtered spectra, we say that the filtered spectrum is co-connected. Associated braided is. This is kind of familiar thing to do, is kind of valence in the T structure. All right, and what's the theorem? Category. So connected. Getting to infinity. Synthetic infinity rings whose underlying filtered spectrum happens to be co-connected in the sense that it's fully phase fluid. These steps. So I think that all justifies very tight analogy with the theory of derived rates. Let me give you one There's sort of one interesting difference between this theory and the theory of derived rings, which is that in derived rings, the free logical and zero sphere, it's the adjoint, polynomial ring, which is connected and coconnected. It's just discrete. In contrast, the free synthetic infinity ring on S00 is co-connected but not connected. That's the principal difference in just the formal development of the theories. Is that maybe some of the intuition from derived rings breaks down in the specific sense that the free things are not discrete. Whether they are connected, and if we trace through the proofs, we say Matthew Mondel's development of affine stacks and derived rings, they really don't use the fact that this is discrete so much as that it's co-connected.
Is S00 the tensor unit?
Yes.
So then the tensor unit is not connected.
So the S00 is connected. Sort of. Okay. This is not the same as the free ring on this. So this is like Z is the tensor unit, which is different from Z genre.
Okay. Thanks.
Then I could go into like a different range of like double credits, because then you somehow when you said you define the free thing, you said you're defining it on the negative series.
Right. So among the negative series are the ones that are not negative, but are both connected and co-connected.
Right.
And the idea is roughly that even on those, you see something on the co-connected.
Same thing, can you describe the even synthetic infinity ring as a deformation of the linked stack?
I mean, it's sort of an animation of even presets. Even though, in what sense would an animated ring be a deformation of a ring?
Sense of.
I'm not. I'm not sure I have an answer to that question goes beyond what's already.
Is it clear whether, so for even pre-stacks, we can restrict them to things that are ln local for some n?
Yeah.
And then I get right conic extent back. Is it a priori clear that what I get when I apply that to a free infinity ring, like, is itself?
I don't know if that's not really clear. I think it might be very closely related to something chromatic convergence for trading in infinity rings. And if you allow yourself that, it's not so far off. So I think that there's some treatment by Rock Gregoric or something which claims that procedure will produce something related to even filtration of the element localization. Okay. All right, so I don't know how much time we have left. I'm going to try to get in a bunch of groups. But they seem to be substantially behind. Let me let me maybe try to prove or sketch some aspects of the proof of this fact, which I think demonstrates a lot of the techniques that are generally useful here. So the fact that co-products of synthetic infinity rings are tensor. So if you unwind the definitions sufficiently, to prove that co-products are tensor products, you're going to do that. Just to prove that if I take the even associated graded and a free infinity ring and some even sphere, the tensor it of the first the sphere, there's the free infinity ring. Okay. This is your starting the free infinity ring. That's it's a kind of formula for the even filtration or the associated gradient of even filtration with speed to proving some property. And maybe you can see a little bit what's at stake here. The even filtration is defined as some kind of big limit. We're taking a limit over all maps to even rings. Now, tensor products behave well with respect to co-limits, but maybe less obviously well with respect to limits. So you need some way of commuting co-limits past limits through this kind of statement.
So you meant show this free function is like the usual function, not the one.
Yes, this is just a statement about the classical infinity rings and their even filtration. They want to indicate some of the kind of fun things that come up in illness that touch on classical effects in homotopy theory. First, I have to set up a little bit of notation. First of all, if R is a graded one ring, or the infinity ring, say first are either the sphere would be a good example we should keep in mind. There's a T structure on graded farm objects. The module is co-connective. If and only if it is an underline. So that's a standard T structure. You made sense of in the graded world also. And the kind of key remark in this business. Curve star either sphere, nothing to curve star either mu. It's much easier because that's just curve star the double speed cosmic filtration in mu. Which is much more understandable thing than this. There's bi-graded homotopy groups record the E2 page of the Adam Novikov spectral sequence. This map is exact. In particular, it preserves co-connected objects. this is not too hard to see if you're kind of familiar with these things. So modules over this is Hubby's stable category of MU star MU co-modules, some kind of derived MU star MU co-module. And this is extracting its underlying module. And there's a little bit of a funny business passing from in code to Q code, but that doesn't affect this statement. And yeah,
Is this true for here? Not.
uh, I think we can talk about it later. I think probably it's something that is for most of them. Okay, it preserves co-connected objects, but then what I want to say is that if the image of a module is co-connected, image I mean this is under the tensoring up functor, so the base change from gross star e s to gross star e venue. If the image is co-connected and the module is bounded above, then the module is connected. So one wants to say that you can detect co-connectivity after base change, and that is almost true, except for this funny distinction between INCO and QCO. If you know that you're dealing with a bounded above module, then you can say that tensor one is not detects co-connectivity. So little lemma you can prove. If C is a co-connected gradient, maybe before I state lemma, I need to state a definition. Module over some R has or amplitude less than or equal to an integer if any tensor over R with n in not equal to n. Okay. We'll see as a co-connected.
Sorry, what assumption are, sorry, because here,
R is a graded ring.
graded E1 ring, right?
What?
Graded E1 ring,
Yeah.
okay, there.
Right. If C is a co-connected graded E1 ring and E has finite star amplitude. Then for any co-simplicial, so B is a C module. And for any co-simplicial C module, a bullet that is level-wise co-connected. The result is that answering And B, and use with the totalization. So this, maybe I won't go too much over, considering the time, so it was extremely elementary and straightforward to check using the connectivity properties. But it's sort of telling you a condition under which you can pass the totalization, like the kind of totalizations that might define this or evil something through tensor. As long as you have some finite Tor amplitude condition. Okay, so now we need to know what kind of things have finite Tor amplitude. When we're looking at modules of the great star evil less. So maybe the interesting proposition that I wanted to mention that correction modulus over their star equals Tor amplitude less than or equal to 0 flows their totalizations. So that, in conjunction with that simple lemma over there, is a very powerful thing for commuting co-limits past limits. And I would like to maybe indicate why this is true. So this is more generally true. Any more regular in a moment created running the store regularity condition is the statement that when R is still regular, every object mod. Remember, there's some T structure on the category of R modules. And I want every object in this filtered code on it. Modules that have finite Tor amplitude. The point is that under this Tor regularity hypothesis, you can test things by only tensoring with objects that have finite Tor amplitude. And for such objects, commuting with totalization is essentially an elementary connectivity. The key claim is that Aristotelius is Tor regular, and this is this Tor regularity condition. For example, if you're looking at discrete rings or graded rings concentrated in gradient 0, it's a condition that's true of Noetherian regular rings. It's a condition that's true of valuation rings. Some kind of regularity of the function. but I just want to say that the results essentially of land weather. The second is the first study that's regular. I just think it's interesting that this kind of classical stuff seems to show up. And the reason is that the modules of the first study that's right again there's something to do with the new star and the modules. I guess they're even. And the claim here is essentially that every even when you start a new module, you filter code on it. Perfect. Even when you start with the modules. Every even and just starting a new module is going to be a filter code of things that are in the fixed subcategory generated by any star itself. And because any star filters finite parameter to it, so that anything made out of it in finitely many steps. So why is this true? It's not immediately obvious, but what is a little bit easier to see is that every even homogeneous the filtered element finally presented even homogeneous. It's much more formal. And the theorem of Landweber is that every finitely presented homodule is in fact perfect. The reason is that Landweber proved every finitely presented these are the homodules. And it's a finite location, it's called Landweber location. With associated data. U star mod I, where I, one of these ideals, you on what this sounds like. And so in particular, it's presenting it as perfect. It's It's not necessarily the case that all of these associated gradient pieces are isomorphic or anything like that. You can always find such a filtration.
What does it mean for an MU co-module to be finitely presented?
Finitely presented as an MU star module.
Okay.
All right, I think that is the end of my time. Let me just maybe indicate that you resolve these things by what are called Wilson spaces. And that might give a clue as to why Hahn and Hopkins work is relevant, if we're studying the Euclidic version of Wilson spaces. And when you resolve these as a totalization of Wilson spaces, the leading things past the tensor products and the stuff like that makes sense.